يعطيكم العافية شباب، بتمنى الجميع بخير. خلينا نبلش بلكتشر 9 اللي هي بتحكي عن المكسر. بتوقع كلكم درستوا ال LNA والأمثلة اللي أعطيتها على الإي ليرنينج على ال LNA، وإذا في حدا عنده سؤال عن المحاضرات السابقة بليز send me an email وممكن نرتب ميتينج على الزوم. Now, mixers. In electronics, a mixer or frequency mixer is a nonlinear device that creates new frequencies from two signals applied to it. For example, a key component of a super heterodyne receiver, as we see in lecture 5, is a mixer used to move receive signals to a common intermediate frequency. So mixers, we translate the frequency from one band to another. Mixers are used for frequency translation of signals instead of using several band pass filters to tune at desired signals. The center frequency of a local oscillator is adjusted so that we have intermediate frequency, and we adjusted the RF by the local oscillator frequency. Now, down convergent mixer, an RF signal is translated to a lower frequency known as intermediate frequency. In up convergent mixers, the IF is translated to a higher frequency RF. How does RF mixer circuit work? An RF mixer is a three-port passive or active device that can modulate or demodulate a signal. The purpose is to change the frequency of electromagnetic signal while hopefully preserving every other characteristic such as the phase and amplitude of the initial signal. Now, a mixer basically multiplies two signals in time domain in order to transfer the incoming frequency to intermediate frequency. Mixing can occur in any nonlinear device such as diode, transistor, and as you see in the equations in the slide, we have up converted components or down converted components. We can choose one of them by using a suitable filter. Simple mixer. A simple mixer is a diode or a nonlinear device. You can imagine a diode in nonlinear equation or a transistor in nonlinear equation. A simple mixer is realized by a switch, which is turned on or off by local signal. So when switch is on, VIF intermediate frequency equal VRF. When switch is off, VIF equals 0, as graphs illustrated in the slide. So, but to recall, why do we convert RF to intermediate frequency? There are several reasons. The main reason, the bandwidth of a filter is proportional to its center frequency. In receivers, like in which the filter is done at the incoming RF frequency, as the receiver is tuned to higher frequency, its bandwidth increases. So the main reason for using an intermediate frequency is to improve frequency selectivity. Noise and linearity. We would like to maximize mixer performance by maximize linearity in the signal path, idealize switching or high slow rates. Third, or finally, minimize noise contribution for the mixer. The design of down convergent mixer is a compromise between the noise and the linearity. So we cannot improve both of them. We have to make a compromisation between the noise figure and IIB3 or non-linear. In a receiver chain, the input noise of the mixer following the LNA is divided by the LNA gain. So we need the gain for the suitable LNA to be high. Now, similarly for the linearity or the IIB3 of the mixer is scaled down by the LNA gain. Converging gain. Now, to study converging gain for the mixer, first, we have to define the convergent gain. The convergent gain is usually defined as the ratio of the IF output power to the available RF power source. So we calculate the convergent gain as the ratio of the desired intermediate frequency output to the value of RF input So it calls conversion gain or loss. Now we called it loss if it is less than 1, or conversion gain when it will be more than 1 or equal 1. Mixer gain is critical in suppression of noise because it is in the second stage in front end receiver. Now low supply voltage make it difficult to achieve a gain or more than roughly 10 dB, so we have to keep that in our mind. Port-to-port feed-through or leakage. Now to study the noise from the mixtures, coupling or parasitic capacitance in MOSFET or BGT cause port-to-port feed-through. The impact depends on architectures. So as we mentioned before, any diode or transistor will accept nonlinearity in its transfer characteristic at sufficient high signal levels so that we can use them as mixers. But this architectures, it may be affected by port-to-port feed-through. The output of nonlinear device may contain ADC terms, RF and local oscillator feed-through, and terms at all harmonics of RF and local frequencies. Only the second order products term reduces the desired output. Now we need some isolation between these ports. Now isolation is a measure of the leakage or feed through from one port to another. The more isolation a mixer provides, the lower the amount of feed through it will be. Isolation is measured at the same frequency as the stimulus, not the converted or shifted frequency. Therefore, frequency offset capability is not necessarily for these measurements. As an example, local oscillator feed through will occur from the local oscillator port to intermediate frequency output port due to parasitic capacitance or power supply coupling, etc. Three main isolation terms are of interest for mixer measurements: local oscillator to intermediate frequency isolations, local oscillator to RF isolations, and RF to intermediate frequency feed through. Why measure isolation? Any unwanted signal or leaking through the device will mix with the desired output signal, creating intermodulation products, adding to intermodulation distortion from the nonlinearity. These unwanted signals may be difficult to filter out. DC offset. If there is a DC offset on the RF input, there will be a local frequency component in the output as well. This requirement is not unusual since many mixer implementations require some bias current, which leads to a DC offset on the inputs. Suppose the RF input is a sinusoidal having the same frequency as the local oscillator as shown. Now, each time the switch turns on, the same portion of the input waveform appears at the output, producing a certain average. Port-to-port feed-through. As we said before, local oscillator feed-through will occur from the local oscillator port to intermediate frequency output port due to parasitic capacitance, power supply coupling, etc. Or reverse local feed-through will occur from the local oscillator port to RF input port due to parasitic capacitance as well. Now, to get the highest performance from the mixer, we must make the RF to intermediate frequency band as linear as possible and minimize the switching time of local oscillator switch. The RF feed-through can be eliminated or reduced by using a differential intermediate frequency output. Now, in the direct conversion case, local oscillator to RF feed-through determined by the symmetry of the mixer circuit and local oscillator waveforms. Now, we have to make a symmetry in the differential. Now, the local oscillator and intermediate frequency feed through usually suppressed by the baseband low pass filter. In this slide, we show that we can still get local oscillator feed through if we take a single-ended output as shown in the figure, or if there's a DC current in the single path. There's often DC offset present, since the output of the transconductance amplifier will have a DC current components. As you see, in heterodyne architectures, if we have a single output-ended output, the local oscillator intermediate frequency most serious, especially if the intermediate frequency and the local oscillator are closed. So filtering them out will make a big problem. Mixer noise. Now, noise figure is generally measured with a wide noise source that is switched on or and off. There are two definitions used for noise figure with mixers, often a source of confusion. Now, we have single sideband noise or double sideband noise. Single sideband noise figure assumes signal input from only one sideband but noise inputs from both sideband. With a single sideband noise figure, the mixer internal noise shows up at the intermediate frequency output from both signal and image inputs, but the excess noise is only introduced in the signal frequency band. The noise figure of a noiseless mixer is 3 dB, so the minimum value of the single sideband noise figure is 3 dB, and it cannot be reduced. With double sideband noise figure includes both signal and noise inputs from both sidebands, appropriate for direct conversion architectures usually. For a direct conversion mixer, only the noise in the signal band is translated to the baseband. The noise figure of double sideband, it could be equal to 0 if the mixer is noiseless. The quantity is called double sideband noise figure. Now, obviously, a double sideband noise figure is easier to measure in regard to single sideband noise. Wideband excess noise is introduced at both the signal and image frequencies. This is perhaps more relevant for direct conversion receivers where the image cannot be filtered out from the signal. Single balanced mixers. Now, we have active or passive mixer implementations. So one can be used passive, which is with gain less than 1, or active with gain more than 1. Each has its advantages and disadvantages. The passive implementation using diodes as nonlinear elements or switches or MOSFET as passive switches always accept conversion loss rather than gain. Now, for single balanced mixers, it provides isolation between local and RF inputs to solve the issues faced by single device mixer type. The simple mixer previously discussed operate with a single-ended RF input and a single-ended local oscillator, discarding the RF signal for half of the local period. We discussed that we can make a mixer by just using one transistor or one diode, but this faces a lot of challenge with board-to-board feed-through, as we explained before. So with single balanced mixers, we provide isolation between a local oscillator and RF inputs as shown in the right figures. Figure right shows a more efficient approach whereby two switches are driven by differential local phases, thus commutating the RF input to the two outputs called a single balanced mixer. The convergent gain is doubled and the local RF feed-through, as we said, at local frequency vanishes if the circuit is symmetric. As shown in this slide, the local oscillator RF feed-through at local oscillator frequency vanishes if the circuit is symmetric 100%. Now, the single balanced mixer provides either local oscillator or RF rejection at the intermediate frequency output, but to be fair, it requires a higher local oscillator drive level. Double balanced mixers, as shown in figure in the slide, it improved to reduce the local oscillator intermediate frequency feed through of the single balanced mixer. We connect two single balanced mixers such that their output local oscillator cancel, but their output signals do not. So, as an advantage for double balanced mixers, both local oscillator and RF are balanced, providing both local and RF rejection at the intermediate frequency output. All ports of the mixer are inherently isolated from each other. Also, it increased linearity compared to single balanced mixer. Also, it improved suppression of spurious products such as intermodulation of the mixer. Also it doubled the gain, or it gives reasonable conversion loss on signal RF. It's about 7 dB. Also broadband in nature and therefore suited to multi-band design, also high intercept points and improved